Hi, everyone. We're so happy to have our lightning talks today. Our first speaker is Sarah Nordahl. Sarah is a graduate student in civil and environmental engineering at UC Berkeley. She's also a senior research associate in the Sustainable Energy Systems Group at Lawrence Berkeley National Lab. She's experienced in LCA modeling, and her current research focuses on evaluating the environmental impact of organic waste management and modeling bioplastic pathways. And we're so happy to have her presenting some of her work. I'll give it over to Sarah.
All right, as Chelsea said, I'm Sarah, and today I'll be talking about the life cycle of greenhouse gas emissions and human health trade-offs of organic waste management strategies. A few acknowledgements. Thanks to all my co-authors, especially Chelsea, who invited me to talk here today, and my mentor, Dr. Corinne Scown, and thanks to LBL, California Energy Commission, Vito at DOE, and Zero Waste Energy Development Company for making all of this possible. All right. Landfilling, as many of you might know, is the most common end-of-life pathway for most municipal solid waste. This is not a particularly sustainable practice and contributes significantly to greenhouse gas emissions. Landfills are actually the third biggest contributor to national methane emissions after ruminants and natural gas production. So local and state governments are trying to pursue zero waste policies to divert waste from landfills and reduce methane emissions. For example, California has a goal to reduce the fraction of organic waste sent to landfills by 75% in 2025 relative to 2014 levels. We're specifically focused on organic waste because that's the component of our municipal waste stream that is producing methane in anaerobic conditions like at a landfill. Gas capture systems, which do exist, are not perfect, so inevitably some of those methane emissions will be emitted to the atmosphere, even at landfills equipped with more sophisticated gas capture systems. We do have a few alternative end-of-life pathway, EOL, that's what that is, end-of-life pathways for organic waste. This does include composting, essentially aerobic decomposition, where we're making carbon dioxide biogenic instead of methane. Anaerobic digestion, where we control that anaerobic decomposition process, in a reactor so that we can capture all the biogas for energy use. We also have incineration, direct land application, and gasification. Incineration doesn't really happen so much in the States, but is a lot more common in Europe. Gasification also produces energy, and then direct land application is just throwing your organic waste onto soil. I'll be focusing mostly on anaerobic digestion, particularly as it contributes to organic waste management in California. In San Jose, there's one of the largest dry AD facilities in the world. It's operated by Zero Waste Energy Development Company, or ZWED for short. For reference, there are also wet AD systems out there, but dry AD is kind of the more relevant, newer technology that most modern facilities that are being built are doing. So that just means a solids loading rate of 20 to 40% instead of less than 16%, like a very liquid stream. So this is a little more solid. ZWED began operating in 2013, and now they process about 100,000 tons of organic waste per year. They get commercial food waste from San Jose and Palo, stuff from grocery stores, cafeterias, restaurants, that kind of thing. They also get residential green waste from Palo Alto and some other sorted organics from local waste processing facilities. As you can see in this little process flow diagram on the left, AD produces biogas and digestate. There's a few things we can do with both of these things. Biogas can be upgraded to biomethane and used for fleet fueling, or it can be injected into the pipeline. We can also use biogas to create electricity and heat. Digestate is the leftover biosolid material in the digesters that can be sent for composting, be used as fertilizer or soil amendment, or other kind of soil amendment type uses. All right, I wanted to specifically focus on ZWED's operation and how they might be benefiting the environmental impact of our waste management system in San Jose. So relative to business as usual practices like landfilling or composting, how do the operations of this facility kind of stack up? So I conducted a life cycle assessment with respect to greenhouse gases and a bunch of other air pollutants that impact public health. That includes NOx, VOCs, SO2, carbon monoxide, ammonia, and PM. And then I'm going to consider a bunch of other hypothetical scenarios in addition to our kind of current scenario at ZWED to see what changes in the current management structure would be potentially beneficial. So yes, focusing a little more on our model scenarios, we have 7 unique scenarios. One where we're doing all landfilling, second where we're doing all composting, and then a bunch of different dry AD scenarios. So this one that's highlighted in yellow is kind of our current scenario reflecting the actual operations at CWED, and all of the other scenarios show some other variation of what we're doing with either the biogas or the digestate. So the biogas, our last 2 scenarios, for instance, in one of them, we're going to be upgrading it to RNG for fleet fueling, and the other for pipeline injection. And other alternative fates for the digestate that we're considering is landfilling, direct land application, and composting, of course. Okay, moving forward. If just a little quick aside, if you want to hear more about the LCA model itself, ask me after about how that input model output model works, but otherwise we're going to get right into results for this talk. Okay, greenhouse gas emissions. In all of the scenarios that involve landfilling, we have higher greenhouse gas net emissions than any scenarios that do not involve landfilling. The composting scenario and our 2 AD scenarios with RNG upgrading all resulted in net negative greenhouse gas emissions because of those composting and RNG offsets. Our electricity dry AD scenarios generally had positive greenhouse gas emissions, but I will say this is really dependent on our offset credit, and we assumed that our electricity production was offsetting natural gas combined cycle production because we're working in California where that's our main electricity source. But in an area where our grid mix is different and there's more coal or oil in our mix, this benefit is going to be bigger and you might actually have net negative greenhouse gas emissions for those scenarios. But given our conditions and where we assumed the most favorable result was RNG production with fleet fueling and digestate composting. And then the results fall are, I'm going to speed through this, but for all of our other air pollutant emissions, composting is dominating emissions for carbon monoxide, ammonia, and VOCs. As you can see, blue is the main color we're seeing in any of these figures, although we see the CHP, flare, and landfill does pop up in the carbon monoxide figure too. For our other pollutants, that's NOx, SO2, and PM, flaring and general AD or landfill operations is what's generally dominating those life cycle emissions. You can see though that there are considerable offsets for diesel and also for electricity production in the case of NOx. And I will say that NOx emissions at a landfill or AD facility tend to be a bit higher on a kind of per unit of fuel input basis than you would see at a natural gas combined cycle power plant because there aren't the same kind of NOx emission controls at those facilities. But then let's put all of these results in the same context. What's the best option with all of our different scenarios? Well, we can use a bunch of social cost multipliers and come up with one standard to compare everything. So here are the social cost multipliers we used for our non-GHGs. And then we used a social cost of carbon of $42 per ton of CO2 equivalents. As you can see here, even though composting was really favorable from a greenhouse gas perspective, it is kind of our worst option looking at all of these scenarios from a social cost perspective. That's really because of the ammonia emissions from composting. So all of these scenarios with composting did end up with the highest social cost, and it's really because of ammonia. So I will say this is obviously super dependent on your ammonia social cost multiplier. So using different models does come up with slightly different results, but generally ammonia is always dominating these results, always coming out with the highest social costs. And so overall, we can conclude that landfilling, not surprising, is not an attractive option at all for organic waste, even in places with gas capture systems like California. AD and composting are better fates for organic waste with respect to greenhouse gases, but as we just saw, composting has a really significant public health impact. That's really related to this whole ammonia issue. Ammonia emissions from composting seem to outweigh any other air pollutant with regard to social costs, but these emissions are less well documented than other emissions, even VOCs or greenhouse gases. So there's more research to be done in this area.